Okay, page 51, 5-1. So what we're going to do is you're not actually, I know it says what is the pH of a 0.35 molar solution. You're not actually going to be doing that calculation, okay? What we're going to be doing is in this unit, you are expected to be able to sort out whether you have an acid or a base or a salt, whether that acid is strong, whether it's weak, and if your salt undergoes cationic hydrolysis or anionic hydrolysis, and then you're expected to know what tool to use or tools to use to find the pH of the solution. So this thing is all about sorting out what is what. So you are going to take a few minutes, and rather than actually finding the pH, you are going to identify, do you have an acid, a base, or a salt? Now, if you have an acid or base, you are then going to answer, is it strong or is it weak? If you have a salt, you're going to answer, do we have anionic hydrolysis? Do we have cationic hydrolysis? Or do we have no hydrolysis? All right? So give those a try. And that must be a video. So give those a try. Okay. Let me find you in here. There we go. Thank you. You don't need to find anything that's funny. You just need to say, do I have a strong base, weak acid, strong base, weak base, I have salt. Yeah, you were not actually solving it this one. I love how they work out the data to the over. Small one. First, they do mine. Why are you shy? Why is that? You know what? So if you want to check the first 4, there. Are there any questions about those first 4? Strong acid, weak acid. We've got HHH, those are all acids, yes? And HCl is the only one that's in that top zone, the gray zone, okay? How do we know that SrOH2 is a strong base? It's a metal hydroxide, and all metal hydroxides are strong bases. What do we have on the right-hand side? What is NH3? It is a weak base. We know that it's not an acid because if we look on our data table, we do see NH3 way the heck down here where it is too weak to be an acid, so it's not an acid, right? So it has to be a base because could it be a salt? No, because salts are made of what? Positive ions and negative ions. Are there any ions in NH3? No, it's a molecular compound. So it's not an acid, it's not a salt. That means by process of elimination, it must be a base. You might also remember that it is one of the, now it's not actually technically one because it's not attached to any carbons, but it looks an awful lot like an amine, yes? And amines are weak bases. Now, if you want to say, how do I know that it's weak for sure? You can go over here and you can say, look, here is NH3 over in the middle of the table on the base side. Therefore, it is a weak base. And the next 3 compounds have metals at the beginning and they have anions at the end. So they are all what type of compound? They're all salts. Salt, salt, salt. And what we have to ask ourselves when we have a salt is there any hydrolysis? Does Ca2 plus hydrolyze? No. Does Na plus hydrolyze? No. Does Fe, and what's the charge of Fe here? 3 plus, because we've got 3 nitrates. 3 plus. Does Fe3 plus hydrolyze? Yes. How do you know that? It's one of the 3 metals that hydrolyze. The Thial. Whoops. I got carried away and left out the L. Thial creepy. Okay, who is the 4th cation that hydrolyzes? Ammonium, NH4 plus. Okay, so yes, iron hydrolyzes, so we have cationic hydrolysis. We'll check for anionic later, but for now we've got cationic hydrolysis. Okay. Now, how about ClO4? What do we have to look at to see if it hydrolyzes? We have to look at its,
how it's strong or weak.
If the conjugate acid is strong or weak. HClO4 is the conjugate acid, and it is?
It is a strong acid.
Strong acid, therefore, ClO4 does not hydrolyze. How about the conjugate acid of Cn minus HCN? It is
A weak acid.
weak. Do we get hydrolysis of Cn minus?
Cn does not hydrolyze.
It does, because its conjugate acid is weak. I know that's what you meant. So, NaCN, we do get the Cn minus hydrolyzes. So we have anionic hydrolysis. And how about our NO3 down here?
Conjugate acid is a strong acid.
The conjugate acid is a strong acid, so it does not hydrolyze. So we only have cationic hydrolysis. In our salt, we have only anionic hydrolysis. And in the CaClO4, what kind of hydrolysis do we have?
It does not hydrolyze.
No hydrolysis. If there is no hydrolysis, what is the pH of that solution?
4.7.
Neutral. Okay, so that is a neutral salt. If we have an anion hydrolyzing, and it's not amphiprotic, do you guys know what anions give you? If they're not amphiprotic?
Basic solution.
It'll give you a basic solution. So anionic hydrolysis will give you basic solution unless the anion is amphiprotic. Okay. So we're going to have a basic salt here. And what about our 4 cations?
Our cations give us an acidic solution.
Cations give you an acidic solution. And if you happen to forget that, if you're like, does it give me an acidic solution? You can go on your data pages and say, how about that, Effie? What does it do? You can go and you can look and say, where are those feel creepy? Ah, they are over where, you know, you have the big long names, hexaaquoiron, hexaaquochromium, hexaaquoaluminum, and of course our 4th cation is ammonium. And where are those ions? They are on the left-hand side. Yeah? And so that means they are acids. How are they acids? It's because those 6 waters attached to them, and that gives them tons and tons of hydrogen ions, so they can behave as acids. Okay, so you'll notice the iron is on the acid side with those 6 waters. Chromium is on the acid side because the H is in the water, make it acidic. And same thing with aluminum. And of course, ammonium is just a regular old acidic cation. Okay? All right. Now, same thing comes to when you're looking for Cn minus and you're like, it's an anion. What if I forget that anionic hydrolysis gives me a basic solution? You can look up Cn and you can say, where is Cn? Cn is over here. What side is that? Acid side or base side?
Base side.
It's on the base side, so it's going to act as a base and produce hydroxide. Okay, so those are several ways of telling what kind of solution you're going to have. Okay? So now we're going to take a look and we're going to say, what tools are we going to use? What tool will we use if we have a strong acid to find out the concentration of hydrogen? What do strong acids do?
They dissociate.
How do they dissociate? They dissociate completely. So what that means is we have a strong acid, it dissociates completely, and so all of the 0.35 molar turns into 0.35 molar H+. This is actually gone now, yes? And so what that means is all we do is we use the stoichiometry, the 1-to-1 ratio, to figure out what the hydrogen ion concentration is. And once we have hydrogen, we can, of course, convert to pH. What if our acid was weak? For example, like HF. What tools do we use when we have a weak acid in order to find the hydrogen ion concentration? Rice and Ka. Okay, Ka. So here is a rice and Ka. Like I said, we're not actually going to do these calculations because I am assuming that at this point, these rice tables look really familiar to you. And you're like, yes, I could write in that assume, x, right? And I can plug it in, I can solve for x, and there I go. Okay? Rice and Ka if you've got a weak acid. And that also goes for a weak acid that is either triprotic or diprotic. How many hydrogens do we take off if we have a diprotic or a triprotic acid?
One.
Just one, okay? So it would look exactly the same as the situation before. Just remember, you only take off the one proton, so you're left with two of the protons still on the H2PO4. Solve, blah, blah, blah. So those are your acids. If it's strong, use stoichiometry. Oh, look, strong and stoichiometry both start with st. Strong and stoichiometry. Things I'm learning 35 years later. So exciting. Okay. And then, of course, the weak little old lady with the bag of rice and the, okay. Now, we have left our strong base, our weak base, we have our no hydrolysis, we have our anionic hydrolysis, and we have cationic hydrolysis. What tool do you think we're going to use for a wrong base? We're going to use stoichiometry. And the thing about strong bases is sometimes it's not going to be 1-to-1. In acids, it's always going to be 1-to-1 because it's only the first hydrogen that comes off to any great degree. Okay, so H2SO4 will just completely dissociate the first hydrogen. But the strong bases come apart completely. So if we say, I need to find pH, I start by saying I have SrOH2 at 0.35 molar, but I know that I have 2 OHs for every 1 SrOH2, so I multiply by 2, and you get 0.7. And I am assuming at this point you can convert OH into H, and H into pH. Or if you prefer, you can take OH, go to POH, and POH to pH. Okay? So that takes care of that. We have a weak base. What will we use to find pH? Rice and Kb. Okay, so here's ammonia. There we are. That's lovely. Blah, 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 blah. We got Kb. I have X's though, and I also have a Kb value, and my table does not give me Kb. How do I find the Kb for NH3? Kw over Ka of conjugate acid NH4 plus equals Kb of NH3. Okay, so other than that, it's all the same. Find hydroxide, convert, and off you go. All right, so that's nice. And CaClO4, if there's no hydrolysis, it's just really easy. It's just going to be pH 7. There's no work to do. You don't have to show anything. You just say no hydrolysis, neutral pH. And now we're left with our salts that are, remember this one, the anion hydrolyzed. And in this one are cation hydrolyzed. Hydrolysis is always a weak situation. Yes? Hydrolysis, always weak. Unless you get like O2 minus. Yeah? Yeah. If you had Na2O, almost always weak, because Na2O would dissociate into, you'd get O2 minus, which is a strong base. Okay, but we're just going to pretend we don't know about that one because it doesn't happen that often. Okay, so we have our Cn minus, and it hydrolyzes. What is hydrolysis? You have to add water. So what you're going to do is you're going to take your anion and you're going to plus water. Okay, and that's going to be the reaction that you use for your rice table, is your anion plus water. All right, and other than that, does it look identical to everything else we've already done?
Yes.
Yes, it does. Do you know how to find the Kb for Cn minus?
Yes.
Yes, you do. Okay. Cationic hydrolysis. So Fe does hydrolyze. And if you're like, I don't remember how it hydrolyzes because it has all those waters and it's super complicated, where can you go look? On your data booklet, because it will tell you what does it form. It forms this big blobby thing here. Yes? H2O5 OH2+, right? And then you can write that in your doodad here. It's producing H3O+. Again, it's a cation, it's hydrolysis, so you must add water. So if you're like, I don't know what to do with this anion, you add water. I don't know what to do with this cation, add water. Do a rice and Ka. Just add water. Just add water. Hydrolysis, just add water. I need a poster to add to my posters. Hydrolysis, just add water. Okay, I got a little giddy there, I'm sorry. At any rate, what that means is that you now have all the tools to do all the calculations for all of these things. Okay? So, strong, use stoichiometry. Strong, use stoichiometry. Cations, do you remember the little cat with the picture of the lemon?
Yeah.
Cationic hydrolysis is acidic. Anionic hydrolysis is basic. Okay, rice and Ka, rice and Kb. Weak acid, rice and Ka, weak base, rice and Kb. And that's it for that. Yay! And we are now moving on to page 62. And this is actually something that we learned before the quiz, I think. Do you remember this? Mixtures of strong acids and strong bases? Okay, so we're going to review it really, really fast. We are going to calculate moles of H+. We're going to calculate moles of OH-. We're going to determine who is limiting and who is excess. And then you're going to figure out how much is in excess by using a RICFA table. And what equation will we use for our RICFA table? We're going to use the net ionic equation, and that's because the net ionic equation will always give us a lovely 1-to-1 ratio, and it makes our calculations a lot easier, okay? You can do it the other way, you just have to spend more time thinking about mole ratios, okay? And besides which, we eventually want the hydrogen and hydroxide concentration anyway, so we might as well work with those from the start. Once you know your moles that are in excess, you divide it by the total volume of the mixture, and that will give you eventually your pH. if you might have to go through, you know, POH, pH, blah, 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 blah. All right. So what we're going to do is we are going to take this problem here. Okay. And I'm going to copy it over here, and you're going to make sure you have a piece of paper. So if you do not have a piece of paper, now is your time to go get one. Okay. Thank you.
I mean, are you offering to me?
Oh, I already have it. Okay. There we go. All right. So what you're going to do for this particular question is you're going to start by writing the formula equation. Then you're going to write the complete ionic equation and the net ionic equation. So you are mixing HCl and BaOH2. So you're going to start by doing that. Please include the states. HCl and BaOH2. I'll start by writing the reactants. If you're stuck, remember, combine your outside ions and your inside ions. And don't be like me and forget to balance it. And I just want to check in with you and ask you if you like my net ionic equation or if there's something I should change about it. Yes, I should always simplify to the lowest possible coefficient, simplest coefficient, because they all have 2. We can go just H plus OH minus gives us H2O. Liquid. Did you guys want to do the rest of the question on your own? I do. And if you want to check your moles of H and your moles of OH, hopefully you remembered that there are 2 OHs in BaOH 2. Yeah, and now you just find this is an F, because it's not an equilibrium strength condition. So it's final rather than equilibrium here. And so now you want to find the molarity per liter of OH. Not the moles of OH, but the moles, this is the moles of OH. You want the moles of OH per liter. You're going to take the moles of OH. Yes. Yes. Your eyes see them in moles rather than word. If you've gotten stuck after finding the moles, remember you're going to use a Ricfa table, and that you're going to use that net ionic equation. And the Ricfa table is done in moles, not molarity. So we are starting out with our 0.01 moles of H plus and our 0.03 moles of OH minus. And then one of those is going to get used up completely. Right? We are on page, let's see, 53, 63. Hi.
Oh, yeah. Oh, yeah.
Right? So we can't say equilibrium. Oh, use it. Yeah. Yes. So if we look at these two numbers, who is going to get used up completely? Is it going to be the H or the OH?
H plus will be used up completely.
The H plus will be used up completely because it's the smaller number. It is the limiting reactant. And the OH minus is the bigger number. It is the excess reactant. Now, if you had a 2-to-1 ratio, you could not tell just from looking at the bigger number or not. Okay, just fair warning. We lull you into a false sense of security in grade 12 because we only do 1-to-1 ratios with limiting reactants. Go to university, you'll be back to doing 2-to-1 ratios, 3-to-5 ratios with limiting reactants, and you'll need to determine who is limiting and how to do the more complex calculations again. But for grade 12, we're like, it's 1-to-1. Isn't that nice? So how much do we use? We use up all of that 0.1. And we end up with 0 moles of H plus and 0.2 moles of OH minus. Now, eventually, we want to find the pH. What do we need to know in order to find pH? If we're working our way backwards, in order to find pH, we would need to have pOH, which would mean that we would need to have not moles of OH, but the concentration of OH minus, which is the moles over the liters. So we have the moles, that's 0.02 moles. How many liters do we have?
We have 0.1 liters of solution.
How did we get that 0.1 liters? Where did that come from?
Looking at the amount in the initial question.
We're looking at the amount in the initial question. We have 50 milliliters and another 50 milliliters, so our total volume is 100 milliliters. So 50 mil plus 50 mil is 100 mil. So that's 0.100 liters, and we get our concentration of hydroxide. I'm not going to show these steps because I'm going to assume that you can do that. Ding. Okay, if you have any problem with that, just drop by during flex, and it's all good. Now, in your book, it does that calculation in millimoles, okay? And the reason millimoles are nice is because you don't have to convert in and out of liters and in and out of liters and in and out of liters, and you end up with a lot less zeros, okay? Are we feeling okay about this kind of problem? Strong acid, strong base, super nice, okay? Now, your brain is going to have to turn inside out, okay? It's going to go on a little roller coaster ride here as we move on to page 66. And we are first going to deal with a weak acid and a strong base. So that is a weak acid, a WA, plus a strong base, an SB. That's all we're going to get through today. We're not going to be dealing with the other case, the weak base and the strong acid. There is no point in doing a weak combo because it gets very, very complicated, the math, okay? So we're never going to do like weak plus weak, what's the pH? We're not going to do that to you because it's too cruel, okay? But we can mix a weak acid and a strong base. And so what we're going to do is we're going to start with this situation where our strong base is the NaOH and our weak base, or sorry, our weak acid is acetic acid. And we are going to partially neutralize it. So if this were a titration, that means we've added enough hydroxide that some of the weak acid has been neutralized, but not all of it. So what this means is that we are before the equivalence point. The equivalence point is when we've neutralized exactly the acid that there is. We haven't added any extra base. There's no excess acid. So if it's partially neutralized, it means we still have weak acid left, okay? Because we haven't used it all up yet. There's still some weak acid there. Could you please write the equation for the reaction of sodium hydroxide plus acetic acid?
Let me find your. Where have I put it?
And it should be right.
There you go. Sure, yeah.
Now, hopefully you guys remembered that it is the H on the end of a COOH acid that is the acidic hydrogen, and that we put that H together with the OH to get water. And that means that the Na gets together with the Ka-choo. Yes? So we end up with Na Ka-choo. Cuckoo Ka-choo, Mrs. Robinson. Do you guys know that song? No. There's a movie called The Graduate. Oh, I probably should never tell you to watch that. It's a little bit. Anyway, but not by today's standards. By today's standards, it would probably be like nothing. It would be an interesting watch for you, like any old film. Have you guys watched many old films?
No.
If you haven't, you should watch at least some just to get a flavor for how different the medium was back then. And if you don't know where to start, Alfred Hitchcock is always good. I do like Alfred Hitchcock.
I think Back to the Future.
Back to no, I'm not talking like 80s old. I'm talking like pre-80s. Because by 80s, it was very soundtrack driven. Before that, there was a lot more quiet space, right? There was not like music all the time. It was like things were happening and it was just quiet. And it's an interesting, not that there wasn't soundtrack, but there was like a mix of both. Anyway, Alfred Hitchcock, if you don't have To Catch a Thief is good. North by Northwest. Rear Window. And if you want something more horror, you could watch Psycho.
Oh.
Okay, these are sort of more thrillers. That's At the Motel, the Seaview Motel. Yes, Norman Bates. Mm-hmm. Oh, yeah. Anyway, not that this is a film studies class, but like Alfred Hitchcock is definitely worth watching. He was an interesting director who, I'm not a huge filmy person, so I don't know all the words, but he did things that were different at the time, and it's a very different experience to watching current movies. So anyway, complete ionic equation. We would have, do we split up the NaOH aqueous? Does it dissociate? Yes, it does, because it is a strong base. So Na plus OH minus. CH3COOH is a weak acid. Do we split it up?
Yes.
Are weak acids mostly dissociated or mostly undissociated?
Well, actually,
Not completely.
I want you to think about those Ka values, times 10 to the negative 6, times 10 to the negative 5. They are mostly undissociated because that power of 10 shows you how much is dissociated. So mostly undissociated. So in a net ionic equation, we leave weak acids together. Okay. See, back in the day, we used to watch all kinds of old movies because it was the only thing on a Sunday afternoon on TV because we had no choice as to what to watch. It was just whatever was on at the time. CH3CO minus. Nope, nope, it's not dissociated. What am I doing? There we go. It's together. And water, do we dissociate water?
No.
No. And how about our salt there, NaCH3COO? Yes. Na plus CH3COO minus, and everybody is aqueous except for the water. So who are the spectator ions here? Na plus, that's our only one, right? So we have OH minus plus CH3 COO H goes to CH3 COO minus plus H2O. Now, we're going to do a Ricfa table here because you'll notice, what have I done with this arrow? What kind of arrow have I drawn? I've drawn a one-way arrow. Now, sometimes people get confused about that because they're like, well, I got a weak acid. Why is it one way? Because of the strong base. That OH, NaOH is strong. It will come and rip all those hydrogens off of the weak acid. So as long as, and I'm just going to put this at the bottom here, as long as one of the reactants is strong, the reaction will go to completion. If both of them are weak, that's the only time you will end up with an equilibrium, okay? And like I said, we're not going to be seeing those very often because it gets really complicated. And if you're still a little uncertain as to why that is, we're going to take a little look at an equilibrium. Here, we can look at the CH3COOH in equilibrium with CH3COO minus plus H plus. And what happens if we add OH minus to this equilibrium? OH minus reacts with H plus, causing the H plus concentration to drop, which causes this equilibrium to shift to the right. Now, what if I add more OH minus? It'll keep shifting to the right until eventually it has shifted completely to the right. Yes? So as long as you keep adding OH minus, as soon as you have the same moles of OH as you did H ions, it will be shifted completely to the right. That's another way of thinking about it as to why it goes to completion, even though CH3COO is strong. It's weak, weak. Oh my God. Okay. Now you are going to see the power of the millimole. let's take a look at our numbers here. We have 2 milliliters of 1.00 molar NaOH. Okay? And if I just want to do a quick calculation here, I can say I have 2 milliliters times, and I'm going to play fast and loose with my sig figs here. I'm just going to say 1 mole per liter. I still have the milli, so that gives me 2 millimoles. Is good? Okay, and because there's one OH here, that's going to be 2 millimoles of OH minus. So we can go and we can put that in our RICFA table. Okay, and I've even written millimoles here, so you don't have to write millimoles every time if you don't want to. Now, how many millimoles are there of the acid? We have 8 milliliters of, remember, what does of mean? Of means times. So we have 8 milliliters of 1 mole per liter. So that gives us 8 millimoles of CH3COOH. Is good? Okay. So over here, we have 8 millimoles. Now this is a 1-to-1. So, oh look, so nice. Who is the limiting reactant? OH minus is the limiting reactant, so it gets all used up. So we're going to use up 2 millimoles, and we get 0 millimoles of OH minus left. We're also going to be using up 2 millimoles of the CH3COOH, and so we get 6 millimoles of the CH3. Oh, I don't want to write that because I'm getting in the way of my other stuff, so I'm just going to write 6 millimoles there. And over here, we're starting with none of the conjugate base, but we end up adding 2 millimoles. So we get 2 millimoles. And this is the weak acid. And this is the conjugate base. You see how that? We've got CH3COOH, and we've got CH3COO, nothing. Weak acid and its conjugate base. We can find our concentrations. We have 6 millimoles of the acid. And what is our total volume? We can go back and we can say we have 2 milliliters and 8 milliliters gives us a total of 10 milliliters. And do you see how at this point now the milli cancels with the milli? Okay, and you end up getting 0.6 molar. We have 2 millimoles of the CH3COO minus, also in 10 milliliters. And so we end up with 0.2 molar. So we have both the weak acid and its conjugate base. So we are still going to use a Rice table to find the pH, but we're going to have to plug in 2 different things now. Okay, we have both the weak acid and the weak base, so we can either use the weak acid equilibrium or we can use the weak base equilibrium. And I don't know why I've made you write 2 lines for it. We're just going to write it once in the rice table. So we're going to use the weak acid because it's easier. You don't have to find Kb. Okay, so CH3 COOH in equilibrium with H plus and CH3COO minus. That is the equilibrium that you get. Now we start with 0.6 molar of the acid and 0.2 molar of the base. How much of the H plus do we start with? 0. And if we're starting with 0 there, which way does it have to shift? Has to shift to the right. So that's going to be minus and then plus plus. And what value should we stick in there? X, because we don't know what it is, right? X, X, X. So we have 0.6 minus X. We have X, and we have 0.2 plus X. It's not that much different from our other rice tables, is it? Okay, so now we write ourselves a Ka, yada, 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 plug in our numbers, yada, yada, yada. This would be a horrible quadratic. What do you think we could do? We can assume X is insignificant, and that's going to be these 2 X's here and here. Assume X is insignificant. And if you do that, look how pretty. Now you're just solving for X. So you grind through the algebra, solve for X. So X is equal to 2.4 times 10 to the minus 5 molar. You can figure out the pH doing your math, and that's it. Okay? And you'll notice it is acidic, and that's because we have excess acid, right? Okay. Now, one more example, because I got through this with the other block, so we're going to get through it us too. This is when we are exactly halfway to the equivalence point. So we have neutralized half the acid. So half the acid is unneutralized. And the other half has been turned into the base. So let's take a look at these numbers here. We start with 2 milliliters of 0.1 molar NaOH. So that's going to be 2 millimoles, yes? Now, I'm going to just let you know right now that calculation we did on the previous page and this calculation, you're not going to be responsible for it. Okay? But you'll want to have seen where the punchline comes from. Otherwise, it won't make any sense. Okay? We've added that NaOH to 4 milliliters, twice the volume of the same concentration. Yes? So how many millimoles is 4 milliliters of 1 molar? That is 4 millimoles. So we can now throw this into a rice table, okay, where we have, or actually a RICFA table rather, RICFA, F for final, because this goes to completion because the OH is strong. And as long as one of the reactants is strong, the reaction goes to completion. So Who is our limiting reactant? OH minus. So we plug in our 2, we plug in our 4 and our 0. These go down by 2. This goes up by 2. And you'll notice if I have neutralized half of the acid, the moles of the weak acid are equal to the millimoles of the weak base. Those are the same. And that's what's magic about that half equivalence point, is that the weak acid and the weak base concentrations are the same. Can you think of another instance when weak acid and weak base concentrations are the same? Where the H species and the minus species are the same? At the transition point of an indicator. And what's true? What else is true at the transition point of an indicator? Ka is equal to concentration of H plus. Whoa, look at this. Now, we're going to find our concentration of our weak acid and our concentration of our weak base. Our total volume for each of those was 6 millimoles. Concentrations are the same because the moles are the same. And we can now throw this into a Rice table. Okay, same math as before, just with different numbers here. And what you're going to see then is that if we assume that X is insignificant, what do we have here? Concentration of the base is the same as the concentration of the acid. These two are the same. And if those two are the same, then the Ka is equal to concentration of H plus at the half equivalence point. So that can actually be something that you use in a titration later on to find the Ka of the acid. Okay, that is the punchline. I'll put the homework up on Teams. And if you want a little bit longer explanation of this, I did record the other class. Do you want me to put that up? No, I'm just going to record this class. Okay, cool.